Hi, this is Stephanie reading to you Chapter 8 from Paul Stamets' book Mycelium Running, and this chapter is called Mycopesticides. So he starts with a little story about his house. He says, "My house, built in 1910 in the middle of an old-growth forest in Washington, was a natural disaster. Thousand-year-old trees created so much darkness in this shadowed woodland that settlers seeking daylight cleared the land so a homestead could be built. When I bought this small waterfront farm in 1984, the remnant of an old-growth stump adjacent to the house sported an artist's conch, a type of mushroom. As I would soon discover, the mycelium from the stump flowed underneath the house in fungal fans that channeled water, rotting the floor joists and setting the stage for insect invasion. When I moved in, I saw that my small house, which rested upon timbers, had soft spots in the floor where fungi were emerging through the carpets. Upon investigating, I was both fascinated and disturbed to find huge waves of brown and white mycelium coursing through the floors and walls of my house. The house was constantly infused with a sickeningly sweet, musty scent, perhaps a perfect abode for a budding mycologist." And then there's two photos on this page. Figure 111 is Dusty Yao, his wife. She's inspecting an aerial termite nest attached to a palm tree in the Bahamas. From these nests, termites march far and wide, consuming wooden structures. And this nest is like almost as tall as she is. It's huge. And then the next picture is of his house. It says, "Our house was destroyed first by fungus, then by carpenter ants, and then by humans with the help of this machine." It's like a big construction digger or something. "The ants followed the path of mycelium and pulverized this house. The author, desperate for a solution, tried something new and received a patent for the idea in 2003. So he goes on to say, "Unfortunately, the spread of wood-digesting fungi, such as the artist's conch, is well known to precede or coincide with termite and carpenter ant invasions. The fungi soften and moisten the wood, setting the table for these munching insects. And so I discovered that the slumping house was under attack by carpenter ants. A friend doing remodeling for me quipped, 'If all the carpenter ants stopped holding hands, your house would fall down.' Each day I awoke to find piles of sawdust on the floor near the walls. Overnight, more of my house had been milled into sawdust by the ants. Visitors showed displeasure at the sawdust raining down upon them, despite my best attempts to make light of the situation. I searched the internet to find information about fungi that naturally parasitize insects, and I began to read about Metaharsium molds, especially Metaharsium anisopliae. Please bear with me with these scientific names. They're almost impossible. Anyway, this one had been used to kill termites. I decided to give it a try and ordered a strain from a commercial tissue culture library. When the culture arrived via overnight delivery service, I opened the package to find a test tube containing a green mold similar to penicillin types one finds on rotting oranges. While all houses have populations of molds and their spores, spawn laboratories such as ours are super clean so that spores are not free-flying, and cultures are kept captive in petri dishes or other sealed containers. I was horrified at the prospect of purposefully letting a mold culture loose in my clean rooms, which would contaminate my mushroom cultures. With the utmost care, I used a needle to pull out a fragment of tissue, placed it quickly and gingerly into a malt-enriched, agar-filled petri dish, and slapped the cover on tight. In a few days, I noticed a whitish circle of growth emanating from the point of inoculation. which was soon followed by green spore zones. After transferring the mold several times, in effect creating downstream quote-unquote generations, I saw something unusual. A white wedge of growth fanning out from the green mold colonies. I'll chase that white sector and see what happens, I thought, hoping that the white wedge of mycelium would have delayed sporulation. The result was a discovery that might retool the entire pesticide industry. From this divergent whitish growth sector, I grew some pre-sporulating Metarhizium mycelium on sterilized rice, a standard spawn medium. I took a teaspoon of mycelium on rice from the laboratory, placed it into a plastic bag, and took it home. I exclaimed to my then 17-year-old daughter, Ladena, that we were going to trick the carpenter ants into spreading my stealthy spawn. Not wanting to place the mycelium directly on the carpet, I requisitioned one of the dishes from her childhood dollhouse. I watched the whitish Metarhizium mycelium on the dish, or I placed it on the dish and put it next to the ants' biggest sawdust pile, assuming that this was a nightly path used by the foraging carpenter ants. Around midnight, en route to the bathroom, my daughter looked down at the dish and gasped. She spotted a swarm of ants all over the little glass dish. Wake up, you've got to see this," she exclaimed. We snuck up to the doll dish and witnessed the ants picking up the kernels of myceliated rice one at a time and retreating into the dark, damp walls of our incrementally collapsing house. Each ant became a distribution vector for the lethal mycelium, a point of inoculation, promptly infecting the nest. A couple of weeks later, my old, decomposing farmhouse was free of carpenter ants and was never reinvaded. I had discovered something amazing. The mycelium of parasitic fungi, prior to sporulation, acts as a Trojan horse, attracting its insect victims. My mind raced with ideas about the implications. By good luck, I told a friend, a be-mushroomed patent attorney, about my carpenter ant experiment. I asked him if I could patent my discovery. With a twinkle in his eye, he answered, "I think you may have something patentable here. Let me look into it." I hypothesized that the house, once treated, has repelled subsequent invasions because the parasitized insect carcasses became moldy from the repellent spores, thus warding off other carpenter ants. Once a wood structure is treated this way, the moldy fungi provide a resident protective shield. So the next section is called The Emergence of Mycopesticides. Swarming over the planet are legions of insects whose diversity boggles the imagination. Current estimates of insect diversity range from 4 to 6 million species, while fungi hover between 1 and 2 million species. According to Dr. Roger Gold, an entomologist at Texas A&M University, about 5% of insects are economic pests. However, biodiversity across the planet is in serious jeopardy. According to an article in the journal Nature, 15 to 37% of current species could die out by the year 2050. Human activity is at the root of this emergency. Cutting down forests and burning fossil fuels cause global warming. Pesticides, herbicides, heavy metals, estrogen-like synthetics, and radioactive waste inject doses of toxins into the biosphere. At what point in this crisis of declining diversity will the survival of the human species be in doubt? Will the ecosystem sustaining human life collapse when we lose half of the world's species, or 90%? We are falling down a slippery slope. with the interests of short-term politics and commerce muffling the voices of alarm echoing from the scientific communities. Pesticides were invented to fight destructive insects and protect crops and structures. However, many of the chemicals used in pesticides, especially the organophosphates, harm non-targeted organisms, pollute water, and impair human health. The toxicity of certain chemical pesticides was not widely known until tons had been dispersed into the environment. Chemical pesticides permeate the food chain. Most Americans, and indeed most people on the planet, accumulate these compounds and their derivatives in their fatty tissues and bloodstream. The need for alternative, non-toxic pesticides is critical, since the medical and ecological impact of toxic pesticides poses a cascading health hazard and a global threat to our biosphere. Fortunately, the EPA has recently banned many of these, and as of February 2004, more than 50 countries, signatories of the Rotterdam Convention Treaty, also limited toxic pesticides. Finding a replacement for environmentally dangerous pesticides will bring us one step closer to preserving biodiversity and saving the ecosystem. The search for ecologically rational methods to control insects has focused on biopesticides, nature-based remedies that cause only negligible collateral damage, or none at all, to other organisms. Biopesticides, especially select fungi, do not pose a persistent threat to the environment after use, in contrast to many conventional chemical treatments that cause long-term damage. The interrelationships between fungi and insects are complex and are only now being understood. Practically all insects engage, consume, or succumb to fungi. However, not all fungi are insect-friendly. We know that thousands of species of fungi called entomopathogenic fungi, that's a hard one to say, attack thousands of insect species. This dance between predator and prey has led to the evolution of survival strategies for both, some of which border on the bizarre. By exploring these relationships, we may be able to adapt new techniques for controlling insects without harming the environment. In 1834, Agostino Bassi noticed that spores of the fungus Beauveria bassiana were causing the disease muscardine, a plague that imperiled the international silk trade. He is credited with conceiving, quote-unquote, germ theory, a major tenet of modern medicine, well before Louis Pasteur discovered the role of microbes in 1858. As more entomopathogenic fungi were observed, often found on the moldy carcasses of dead insects, the pesticide industry explored the use of fungal spores as natural insecticides. Since the 1990s, several patents have been awarded exploiting these mold fungi, raising expectations for treatments in the emerging field of entomopathogenic mycology. Most of these mycopesticidal patents target an insect species using a fungus strain with or without an effective delivery system. Species in the genus Metarhizium, especially Metarhizium anisopliae, a green mold fungus highly prevalent in soils, in the genus Beauveria, and some species in the genus, I have no idea how to say this, Paleosomiaces, hosting many white mold fungi, have earned the most attention from researchers. When insects come into contact with spores of these entomopathogenic fungi, the spores attach to the insects and germinate, boring hyphal pegs through the insect's exoskeletons using chitin-dissolving enzymes. Other portals of entry include the respiratory tract, anus, and mouth. Once inside, the mycelium forks and runs through the internal organs, interfering with the creature's metabolism and causing malaise, necrosis, and death in a few days. The insects, looking mummified with fuzzy mycelium, then become a launching platform for further sporulation. With some species of those various scientific names, a tiny club-shaped mushroom classified in the genus Cordyceps can sprout from the dead insect carcass. This is an example of fungal dimorphism. This organism can express itself in either two forms, as a mold or as a mushroom. And I'll take a moment to tell you about the pictures on this page. So figure 113 shows mycelium emerging from a carpenter ant. This ant ingested the pre-sporulating mycelium and became mummified. The infection here came from within. And it shows this ant close up with lots of white fuzzy stuff on its outer shell and stuff. The next figure shows Cordyceps myrmecophilia mushroom fruiting from the carcass of carpenter ants of the genus Camptonotus. Some species of Cordyceps can express a mold state, such as the green mold Metarrhizum anisopliae, which produces spores highly pathogenic to ants, termites, locusts, mosquitoes, and mites. And the last picture on this page is of Cordyceps fruiting from a carpenter ant in Costa Rica. The ant, once infected, has the irresistible impulse to climb to the top of the jungle canopy. Once it has ascended and locks its mandible into a leaf, it dies, whereupon a mushroom sprouts from its carcass. This behavior ensures that the spores of the mushroom will spread far and wide by the winds. And it shows there's this long stalk and a little mushroom body coming directly out of the head of the ant. Okay, and then he continues on, I think, with the same story about the ant. So sorry about the repeat, but he says one species of Cordyceps, when it infects the carpenter ants, compels the insect to climb to the canopy of the Costa Rican cloud forest where it resides. Once it has ascended, the ant locks its mandible into a leaf and dies. A cordyceps mushroom erupts out of its head by releasing as yet unidentified chemical compounds and compelling the insect to ascend to the top of the forest canopy. The mushroom can release spores that fly far and wide, ensuring wider distribution than would be possible near the ground. Many fungi use insects as vehicles for distribution and later their carcasses as centers for spore production. And then on this page, we have figure 116, which is the cordyceps life cycle, which just shows where it starts from ascospores and germinates and goes all the way to the ant. And then in the last part of the life cycle, those mushroom bodies release the ascospores again. With social insects, those that have a queen, such as ants and termites, the partitioning of fungi-infected members is critical to the nest's survival. The populations of some termite and ant nests number into the millions. In order to protect these large nests, the insect communities set up a sentry system guarding the queen and her brood. Some entomologists have termed these nests quote-unquote factory fortresses, with soldiers throughout the nest on high alert to prevent entry from enemies, including infected members. If an infected individual is recognized, it is promptly killed and placed in a graveyard away from the nest. In other words, the insects know that the plague is nearby when they sense or smell it, and they immediately mobilize to prevent infection of their colony. Millions of years of common evolution have allowed fungi and insects to learn to recognize each other and engage in a constant biochemical dialogue. Worldwide, termite species number at least 2,500, of which about 150 species can attack buildings. But within those 150 species, only a few cause widespread economic losses. There are nearly 600 species of carpenter ants, of which about a dozen attack buildings. Carpenter ants are nature's way of recycling wood. Carpenter ants and termites dance with fungi in debris fields and wooden buildings. Above-ground colonies of Formosan termites can contain 500,000 to 3.5 million individuals. This species does not need to forage outside the infested structure, unlike its subterranean cousin Reticularis philippes. The damage primarily to buildings caused by native subterranean termites in the U.S. alone exceeds $10 billion per year, while the damage from the imported Formosan termite exceeds $1 billion annually. Whole neighborhoods and even entire cities, such as New Orleans, are being consumed. That city loses $300 million per year to termites, with forecasts of greater damage as the colonies penetrate deeper into the city's wooden infrastructure. On an individual level, the threat of losing one's house, for most people their largest single investment, can drive a homeowner to spend whatever is necessary to prevent damage by insects. This drive to protect one's home has been a major economic stimulus for the pesticide industry and a global market for insect defense measures and cures continues to spur the invention of new pesticides. The environmental persistence and inherent toxicity of conventional pesticides have only recently been recognized. The market value of the pesticide industry in the U.S. has swelled to $9 billion. Of that, 5%, or $450 million, is from biopesticides. The biopesticide market share is increasing about 15% per year. The pesticide industry has traditionally employed monitoring stations to capture and identify the insects infesting wooden structures. Once the type of invasive insect is identified, a treatment strategy is chosen. A current practice, declining in popularity, is to tent and fumigate a wooden building with a dose of toxic gas, or to heat it with portable propane-fueled heaters. These types of techniques succeed temporarily at best and are generally disappointing, since the bugs usually come marching back. Plus, chemical treatments can be toxic to humans, other animals, and the environment. The use of entomopathogenic fungi as a biological weapon against insects has many advantages, but also faces obstacles. Several companies have expended a great deal of money to develop spore delivery systems, especially using the entomopathogenic green mold Metaharsium anisopliae and the white mold Bouveria bassiana. However, spraying an entire building with spores is impractical and unlikely to assassinate the queen of the colony. Although captive insects are easily infected with spores in the laboratory, insect communities in nature have developed sophisticated strategies for defending themselves against contamination. In groups of social insects, spore-carrying workers are refused entry to the nest, with several tiers of guards preventing any disease-bearing insects from entering. Throughout the late 1980s and 1990s, pesticide researchers tried to place spores in bait or treatment stations fine mesh brushes at portals where entering insects would pick them up. This way of killing insects looked promising at first, since entomopathogenic spores quickly penetrate the exoskeletons of termites or ants upon contact. But the colony's aversion to pathogenic spores and the insects carrying them stymied commercialization of these insect control stations. Although incidental contact with free-flying or soil-borne spores may succeed to infect individual insects, natural selection has given a decided advantage to insects that can detect entomopathogenic spores and avoid them. A fungus that would always alert its desired target insect with smelly spores would be selected against, unless there was an alternative strategy for tricking the insects to engage the fungus. I surmised that since the insects can detect infectious spores, essentially, quote-unquote, knowing a mold plague when they sense or possibly smell one, the fungus also knows that the insects know. I realized that I could create a temporary sporeless state in Metarhizium or Beauveria that not only lacks the repellent smell, but also actually contains an attractant. In the course of growing Cordyceps sinensis, a fungus traditionally used in Chinese medicine, I was intrigued by the idea that it could also serve as an insect pathogen and that it expressed different forms of mycelium. My curiosity led me down a path of discovery not taken by other researchers in the field. When I first obtained cultures of the green mold Metarhizium anisopliae for my experiments with carpenter ants, I selected white wedge sectors of mycelium that lacked or had delayed spore formulation, and I made descendant cultures. After successive transfers of the selected pre-sporulating mycelium, its whitish form soon dominated. In culturing these mold fungi, and through further generations of transfers, I isolated a non-sporulating myceliophenotype. These sectors initially appear as white V-shaped wedges of growth that gradually lose the ability to produce spores. I pursued these pre-sporulating growth forms in vitro and soon discovered that the sporeless mycelium, still lethal to insects, emits attractants and feeding stimulants. Although it is possible that ants and termites might recognize over time that the pre-conoidal mycelium is pathogenic, its occurrence in nature is rare compared to the sporulating state. That we have many entomopathogenic fungi to tap into, essentially meaning that moldy insects give us a constant reservoir of new strains, makes recognition by the insects difficult because we can constantly switch up the strains. Since insects avoid known lethal spores, attracting them to pre-sporulating insecticidal fungi has obvious advantages, including that the insects themselves could become agents for dispersing this insecticidal fungus, which could later sporulate throughout a colony. Soon after my pilot test on my crumbling wood-framed house, I initiated a series of research trials at Texas A&M University's entomology department under the guidance of Dr. Roger Gold. These trials showed that Formosan termites, eastern subterranean termites, and fire ants were attracted to the mycelium, fed upon it, and carried fragments back to the nest. In 2 to 3 weeks, they died from fungal infection. In choice tests, termites preferred the mycelium to wood, and in one alarming example, fire ant workers enthroned the queen on a bed of mycelium, where she soon expired along with her subjects. With termites, it appears that the mycelium kills the large protozoa in their digestive tract, which thwarts their ability to metabolize cellulose and starves them. The insects sicken and become susceptible to infection by the fungus, both internally and externally. Furthermore, we found that even water and ethanol extracts of the pre-sporulating mycelium on rice yielded a powerful attractant and a feeding stimulant. Through cereal dilutions, we discovered that our baseline extract worked best after being diluted with water, thus reducing production costs. And I hypothesized that native-born fungi from an already infected termite colony are more attractive to that species of termite than to others. In many cases, Metarhizium strains from one insect species colony did not attract other insect species. We also determined that only some strains of Metarhizium anisopliae produce species-specific attractants, which may lead to the design of products to target specific insect pests. This discovery, that the extracts made from pre-sporulating mycelium of entomopathogenic fungi may have greater implications. I also found that Beauveria bassiana produces attractants prior to sporulation. Many other genera of entomopathogenic fungi and species in the order Entomopathorales, for example, are likely to produce similar attractants, feeding stimulants, and trail following agents for the insects they target. And just an overview of a couple of the photos. Figure 119 shows ants swarming on pre-sporulating mycelium of an entomopathogenic fungus. After contact, the ants become infected and spread the mycelium, which subsequently regrows, resulting in their death. And then he has another figure of various, it looks like petri trays or some kind of experiment. And it says here, when an extract from a pre-sporulating entomopathogenic mycelium grow on rice is placed on cellulose, termites tunnel to it, ignoring 3 non-treated controls. And you can kind of see there's one where there's a very clear tunnel going right to the dish in the middle. Okay, so continuing on, we have 2 more pages to go, guys. Almost done. So follow-up research at Texas A&M determined that the pre-sporulating mycelium of Metarhizium and Beauveria showed other unexpected properties. Termites seeking wood burrowed to the location of the mycelium and stopped. The entomologist viewed this quote-unquote arrestant behavior as a unique benefit of our natural pesticide. After contacting most other pesticides, the insects continue on their destructive path. But with our method, they penetrated no further. Additionally, termites that contacted the mycelium then recruited other individuals to travel to the pre-sporulating mycelium, who in turn solicited even more insects. The compounding effect of recruitment means that a little mycelium can go a long way, as opposed to contact poisons such as pyrethrin, which quickly kill the insects before they can return to the colony and thus must be used in large amounts. This discovery of how to use the green mold Metarhizium for controlling insects is a splendid example of quote-unquote green chemistry at work. A fungus can entice an insect to carry and cache it as food before it is recognized as a pathogen. The active constituents causing attraction, feeding, dispersion, recruitment, and eventual death have not yet been molecularly characterized. Characterizing these behavior-modifying agents may not be as simple as discovering, for instance, a single antibiotic. We may eventually find that rather than a single molecular compound causing such diverse effects, suites of synergistic compounds work in concert, like a combination to a safe. Time will tell. The benefits of this discovery, the economic and ecological impact, may prove extraordinary. Mycelium Running does not infect plants, mammals, fish, bees, or other beneficial insects. For this reason, the EPA has encouraged the study of Mycelium Running as a biopesticide. Other benefits include the following. And then he has a long list of bullet points here, so bear with me. Other benefits are replacing toxic pesticides with an effective natural method for eliminating termites, ants, and flies, protecting groundwater and habitants from contamination by toxic pesticides. 3, recruiting the pesticide insects to implement their own destruction. 4, using the genome as an indigenous source of new strains, thus limiting tolerance buildup. 5, minimizing potential harm to non-targeted insects while precisely targeting unwanted insects. 6, providing attractants to the pesticide industry that allow insect contact with spore and chemical-based treatments, lowering the amount required to be effective. 7, affording long-term protection of treated sites because after treatment, spores repel future invasions. 8, allowing use of structural building materials otherwise susceptible to insect destruction, reducing the need for termite-resistant tropical hardwoods from rainforests, for example, while retaining jobs and helping the U.S. wood products industry. And lastly, saving diverse biological communities. So on December 9th, 2003, with the help of my attorney friend, I received approval from the U.S. Patent Office for a patent on this biotechnological breakthrough for attracting and killing Formosan termites, eastern subterranean termites, and carpenter ants. On October 17, 2006, I was awarded a second patent using these pre-sporulating fungi for controlling all social insects, which are estimated to be nearly 200,000 species. I have pending an expanded set of divisional patents, basically derivative patents from my first patent, within the continuation in part application. Recent trials show that fungus gnats and blowflies are attracted to this mycelial extract, which strongly suggests that this technique may also be effective against non-social insects. In addition to Mycelium Running, several other entomopathogenic fungi show similar activity using the patent-pending techniques in the expanded continuation in part patent. The future of this green mycotechnology looks highly promising for treating insects that undermine structures, decimate crops, and carry diseases. This type of green technology confronts the paradigm articulated by the motto of the 1950s and 1960s, quote unquote, better living through chemistry. Clearly, the chemical miracles worked in the mid-20th century had a devastating impact on environmental health. Big profits trumped good science, and as a result, future generations will have to deal with more pernicious forms of pollution. Any revolutionary technology, such as the techniques described in this chapter, will be seen as a threat to conventional industry. Therefore, I follow these guiding principles when signing industry licenses for my mycopesticide patents. So again, we have another fairly long list. One is to develop effective and environmentally safe methods for controlling insect pests utilizing fungi. My philosophy is not to wage war against the insect kingdom, but to enlist fungal allies for the intelligent, natural, and localized control of targeted insects when and where they threaten people, buildings, jobs, or the environment. We seek balance, not extinction. Number 2, to license the mycopesticide patents to those who will best promote my nature-friendly alternative to toxic chemical treatments, and not to license this technique to those who would suppress or delay its use in order to maintain consumer demand for toxic chemical treatments. Number 3, to respect the intellectual property rights of all peoples and to commercialize fungal strains traditionally used by native peoples in natural pest control techniques, but only with their consent and participation. I am opposed to biopiracy. And number 4, to encourage the use of environmentally safe mycopesticides in impoverished countries to control previously uncontrolled pests, or to reduce the use of dangerous chemical pesticides, to provide financial support to nonprofit organizations that can manage and promote the use of mycopesticides in poverty-stricken communities and environments that are at risk from pests. And lastly, to respect the sanctity of all species, to preserve and honor biodiversity, and to protect the environmental health of all inhabitants. And here is the last paragraph of the chapter. Since entomopathogenic fungi, especially in the form of mycelium, can be projected via many carriers, for example, wood chips, sawdust, paper, cardboard, biodegradable fabrics, and many agricultural waste products, I envision landscapes customized with mycelium matrices. These would be populated by fungi that target specific insects and the diseases they carry, forestall or prevent pest outbreaks associated with livestock and farms, and stop beetle blights from spreading across forests, all while preventing and cleaning up pollution. The end. Thank you for joining us for Chapter 8.